That's what we discussed. Now, one more thing. When we are talking about the heating effect of the wires or anything, heating effect is directly proportional to density of the material. Remember this. Okay. So that's the reason for the nichrome wire here, because heating is directly proportional to the density, resistivity. Okay. So this is one of the important points. And another, I told you in the class that brightness is directly proportional to the power. Okay. So many questions are there related to power. Then see, two bulbs are rated P1, P2 if they are connected in series and in parallel across a supply of V. Find the power dissipated in the two combinations. See, when they are connected in series, of course, the potential will be different, right? And when they are connected in parallel, the potential is going to be the same. So it says two bulbs are rated P1V, P2V, means potentials of both the bulb are the same. So in series connection, see, whatever you get for the resistance, it will be just opposite. Means 1 by P1, 1 by P is equal to 1 by P1 plus 1 by P2, and P is equal to P1 plus P2. The reason is that P is equal to V square by R. Your power is inversely proportional to R. And voltage here or in the other cases, this is the constant. It is given voltage is same in both. So power is inversely proportional to the resistance. Okay, so first three questions I think were given. Fourth wasn't given, but let us just discuss this. Okay, two wires of same mass having ratio of lengths 1:2, density 1:3, and resistivity 2:1 are connected one by one to the same voltage supply. You have to calculate the rate of heat dissipation in the first wire is given as 10 watt. The second one is asked. Means in the first one, the rate of heat dissipation is given, that is 10 watt. What is 10 watt? The power is given. And it says you have to find out the same thing for the second wire. Now look, when we're talking about the resistivity, here it says same mass and density. Yes, this will give you an idea about what, right? So two wires of having same mass have the ratios of the length as L1 by L2 is given as 1 by 2. Density ρ1 by √2, or in fact, I'll just take it as D because resistivity is also there. So density, I'll write D1 by D2 is given as 1 by 3. And resistivity is 2:1, means ρ1 by ρ2 is given as 2 by 1. They are connected one by one to the same voltage supply. Voltage is also the same. See, you have the formula R is equal to rho L by A. Okay, voltage is the same. It means we require power, and power is given. Look, what is given? In the formula, you have the voltage same. Power you have to calculate. So at least you need the resistance. So how will you calculate the resistance? Resistance will be calculated from here, class. This is R1. Density will be there, length will be there, area will be there. It says same mass. So look, the density is nothing but mass by volume, right? Density is mass by volume. So that's why same masses is given. It means density and volume are inversely proportional to each other. Okay, now see, volume is equal to area into length, right? Volume is equal to area into length. So from here, if I want to replace area, I can write this as volume divided by length. So I'll put it here. So resistance is going to be rho L square by volume, right? Now volume is exactly inversely proportional to density. So whatever is the ratio of density is the reciprocal ratio of the volume, 3:1. So from here you will get R1. Similarly, you will get R2 because density's resistivity's ratio is there, length ratio is there, and volume ratio has been taken from density. Then similarly, you will calculate R2 rho 2 L2 square divided by V2. Resistivity is also given, length and volume from here. Once you have R1 and R2, plus you need the power. P1 by P2 will be R2 by R1. Why? Because V square will get cancelled, same voltage. So from here, whatever other resistances from here, one power is given, P2 has to be calculated. Did you get this question? How to solve? Hence, did you get? Or should I repeat any particular point? Yes, class. Yes, no, what? Is that clear? You need me to repeat? Is it clear?
Yes.
Okay, and what about Aisha and Marwa? This fourth question, is it clear? Because I didn't give this as a homework. I wanted to discuss it in the class. Just quickly write down the points. Don't solve it. Just quickly write down the main points and then we shift to the Wheatstone bridge. And let us start with magnetism today. Just quickly write down the points of this question. Aisha has given Ohm's law's assignment. Marwa has given the power one. Ubaidullah, I haven't received your assignment. Class, when you're uploading the test, please check the PDF. Ali, I think this has happened twice. This is the second time it is happening. You just shared a single page. That was in between. Nothing was there. Even I couldn't assess you based on a single question. Please be careful. One single page, I'll be marking 0. That's what I did. And I know you had attempted the test and that was a mistake. You didn't just do that much portion. You have a complete PDF. You had it. But earlier also same thing happened, Ali. Why don't you just check the PDF? All of you, not just for Ali. Ali, I think you have shared it on WhatsApp, the same test. Be careful from the next test onwards. At least attach the sheets. Whatever score you get, that's a different thing. But at least attach the sheets properly. Just let me know done class so that we can flip. Okay, others done apart from Ali. Okay, Aisha done, Ali done. Marwa and Ubaidullah completed.
Yes, sir.
Yes, ma'am.
Okay, then. The proper solving part you can do later. I hope you've just written it roughly so that when you revise and if you get stuck, you can just prefer it. All right, so we were discussing Kirchhoff's law and we've almost discussed the entire portion. We just have a derivation of the Wheatstone bridge. In capacitance part, I discussed with you that the balancing condition of a Wheatstone bridge is when the ratio of R1 by R2 will be equal to R3 by R. Okay, this is what is meant by the balance condition. So in case of Wheatstone bridge, you just have to derive it using Kirchhoff's law. So if the question comes, this one will be easy and I'll suggest go for this one because here the equations will be formed very easily. Okay. So let's say a main current has been taken out from this cell. That is current I. Now some amount of current will go across this branch. Let's say this is some point A, this is point B, this is point C, this is point D. Now look, some amount of current will go in this branch. Let's say I1 amount of current goes across this branch. So class, across this branch, what do you think? Which is the amount of current that I should take across this AD? Yeah. I current was coming, I1 has gone across AB. So what do you think is the value of current across AD?
I minus L.
Yes. Ali and Ubaidullah correct. I minus I. Yes. This will be I minus I. Now look, let's assume across this galvanometer some amount of Ig current flows. Ig, so just to distinguish it that this is the current flowing across the galvanometer whose resistance is also G. Why am I not focusing on this so much? You'll realize it here only. Ig is, let's say, the amount of current flowing. I1 was coming, Ig has gone. I1 amount of current was coming, Ig has gone to the wire. So rest of it will be I1 minus Ig. Now look, I minus I1 was coming, Ig is coming from here. Can you tell me what should be the current across this branch? I minus I1 coming from here, Ig coming from here. Class, this is easy. Yeah,
I minus I1 plus I.
very good, Ubedullah. Yeah, Ig is coming, I minus I1 is also coming. So they'll eventually get added up. When amount of current leaves, so you subtract. I1 was coming, Ig went, so you subtract that. When Ig is coming, I minus I1 both are coming, so you'll add it. So this becomes, in this branch, we'll have I minus I1 plus Ig. Look here, class. I1 minus Ig is here and minus I1 plus Ig. They'll get cancelled. We'll be only left with I current. So it means distribution is correct. KCL has been applied. Do you all agree till here? Is this fine?
Last part I am not.
This you told me I minus I1 plus Ig, Ubedullah. Now see, I minus Ig is coming from here. Sorry, I1 minus Ig is coming from this side. And from this side, which you mentioned, is coming I minus I1 plus Ig. So what will be the total current? Ig gets cancelled, I1 gets cancelled. Are we left with I? Yeah?
Yes, ma'am. Understood.
All right then. Let's say we are moving, let's move along the current only. Let's go clockwise. And this is also clockwise. Let's go clockwise in both the cases. Remember, we are just proving what's the balancing condition. And one more condition that I'll tell you. But first, let us just write down the equations. In the loop, let's say A, B, D, A. In loop A, B, D, A. All right. So we are going from A to B. Okay, this is the movement A to B, B to D, D to A. This is clockwise here. So if you are going clockwise here, A to B, see you are moving along the direction of current, right? Along is negative. For along, we write negative, so minus. What's the voltage? Current into resistance. So we get I1 into R1. Come down here. This is, again, we are moving along the direction of current. So it will be minus Ig into G. Now see, here we are moving opposite to the direction of current. We are going from D to A while the current is moving from A to D. So this will be just opposite direction of current. So we'll take positive. This will be plus R3 into I minus I1 is equal to 0. Tell me, class. This equation is fine.
Ma'am, that G is also resistor.
It's the resistance of the galvanometer. Yes, that's the resistance. Okay.
What is galvanometer?
Galvanometer is a device that detects current, whether current is present in your circuit or not. Okay.
Yes, ma'am.
See, in the balancing condition, no, because we are referring to the balancing condition. So in the balancing condition, the Ig's value is 0. There is no current that passes through this galvanometer. So basically, you just have to make Ig 0, and here you have the equation. We'll have the equation as minus I1 R1 plus I minus I1 into R3 equal to 0. From here, let's make this positive. This will be I minus I1 into R3 is equal to, this goes on the opposite side, it will become plus class. I1 into R1, that's the first equation. See, first tell me, have you all understood till here or anything bounced back? from your head. Is this clear till here to everyone? Okay. Others? Marwa, you getting? Yes, Marwa, you there? Okay. All right. Now let's come to the second loop. We are going from B, C, D, B, right? Yeah. In the loop B, C, D, B. In the loop B, C, D, B. Let's follow the rule. From B to C. If I am going, see, I am going from B to C. Current is also going from B to C. Aisha, can you tell me, will it be negative? Potential will be negative or positive for B to C?
Positive.
Positive. We are going along the direction of current.
Negative.
Negative. We are going along the direction of current. So this will be minus I1 minus Ig into R2. Minus R2 into I1 minus Ig. Okay. Then we are coming from C to D like this. Okay, we are going from C to D. Marwa, positive or negative potential? We are moving from C to D. Current is going from D to C. We are moving from C to D. Positive. Yes. See, we are moving in the opposite direction to the current. So it will be positive. Plus I minus I1 in I minus I1 plus Ig into R4. R4 into I minus I1 plus Ig. Is that it? Yeah. Okay, Ali, you tell me, we are going from D to B. Should the voltage be positive or negative?
Positive.
Positive, because we are moving against the direction of current in the opposite side. Yes. So it will be plus Ig into B is equal to 0. I think that was required. Now let's make the value of Ig 0 because it is there in the balancing condition. So this becomes 0, this becomes 0. That's it? No, this also. Yeah. All the Igs are 0. See what is left now. This says minus R2I1 plus this says R4 into I minus I1 is equal to 0. So we can say R4 R minus I1 is equal to R I1 R2. That's our second equation. We already saved our first equation here. We have our second equation now. If we take the ratio, let's say divide, let's divide 1 and 2. So the first equation is R3I minus I1 is equal to I1 into R1. While the second equation is R4I minus I1 into I1 by R2. I1 gets cancelled, this bracket gets off. So R1 by R2 is equal to R3 by R4. This is the balancing condition which you have to derive in the exam. Tell me, class, is that clear? Did all of you understand this?
Yes, ma'am.
All right. Okay. All right then, please write it till here. And if there is any part you want me to repeat in between, please just unmute yourself, clarify your doubt. This is the derivation for the Wheatstone bridge.
Ma'am,
Yeah.
can current go from D to B?
Can current go from D to B?
Yes.
Yeah, then you have to change the arrangements. Same answer, you'll get the same answer. See,
So
that's
we
what,
can assume in that way also.
yeah,
So we can assume in that way also.
yeah. See, your currents will change then. The variables will change. Eventually, you'll get the same result because Ig will be 0. If you change the direction from D to B, so it will be different. Here, I1 plus Ig will be there. Here, 1 minus sign. So again, here you will subtract and this Ig won't be here, it will be here. You'll get the same thing. Same calculation, same result. That's what I say. In Kirchhoff's law, you are independent to choose the direction of current until it's correct. And you can just write the variables the way you want to write. If you want, you could have chosen this side as I1 and this side as I minus I1. Same answer you'll get. You are bounded in KVL, Kirchhoff's voltage law, because there is no option once the current is decided. Till the time the current isn't decided, you are distributing the current, you can distribute it in freehand, and then you can just take the turns according to you, clockwise, anti-clockwise. Till here, you are independent. After that, you need to abide by the law. That is along an opposite one. That thing you have to take care of, and for the cells. Except for that, the distribution of current is just up to you all. However you wish to distribute, it's just that in the same branch you will get the same amount of current. In the board exams, usually tough circuits are not given. The toughest one which I find is there in the NCRT, which I discussed in the last class. That's a very lengthy one. Yeah, Vedula.
Why is Ig 0?
Ig, because remember I told you in capacitance, the potential difference is 0 across the galvanometer's branch in a balanced condition. That's what is known as the Wheatstone bridge. So that's why we are taking, since no current is passing, so you can just write Ig is 0. Okay.
Yes, ma'am.
Done?
1 minute.
And now,
Yes, ma'am.
all right. So see, let's start with chapter 4. So now this is your magnetism unit. So two chapters are there. Moving charges in magnetism and matter. So this is chapter 4, that is moving charges, moving charges and magnetism, which is basically, this is also known as magnetic effects of electric current, because we'll now be talking about magnetism. So first, the basic concept, which is your magnetic field. The way we have studied about the electric field, this is similar to that. If I draw a magnet here, let's say this is a bar magnet. So there are certain lines of force that travel across these. Let's say this is the north part, this is the south part. So there are certain lines that enclose this, and they form closed loops, which is the differentiating point from the electric field lines. They travel within the magnet also. We will see about these lines and discussion in the next chapter, chapter 5. So there are various lines across the magnet. So these are the magnetic field line. These are the space where magnetic properties can be experienced. Means if I have a bar magnet here, let's say this is the north part. So technically north and north should repel each other. But here this north and north, because it is out of the magnetic field, it is not included there. So this won't have any effect. Till the time the North Pole or the South Pole is touched within the magnetic field, the magnetic properties couldn't be experienced. Now, as I bring the north part of the bar magnet here, they'll be attracted because this is lying in the vicinity of the magnetic field. So magnetic field is what? It's basically space around a magnet where you can experience all the magnetic properties. So in the first two chapters, we saw how the current was static, charge was static, current wasn't there, charge was static. Then when the charge started flowing, we talked about current electricity. Now, when the current is produced, it will lead to magnetism. That's why this sequence is this. And regarding magnetic field, you should know how it is represented. It is not represented through M, this is represented through B. And it's a vector. So B with an arrow on its head, this is the vector symbol. SI unit is Tesla, represented through a capital T, while the CGS unit is Gauss, represented through capital T. And class, I'll tell you, like in Coulomb's law, when we started with electric charge, that time I told you, even in the backup classes we have done that Coulomb is the SI unit for the charge, stat Coulomb or electrostat unit is the CGS unit, but you will hardly find it anywhere. Most of the time you have the Coulomb as the main unit, but Gauss and Tesla both are used. Most of the questions have Gauss as well. Even in your chapter 5th, you will see this. So 1 Tesla is equal to 10 to the power 4 Gauss. This is an important conversion now because this might be used. And if you have Gauss given, then use 10 to the power minus 4 Tesla, vice versa. Okay. So this is what you should know. And let me just talk a little bit about the sources of magnetic field. See, in class 11, you had a chapter structure of atom in chemistry. So you must have studied where you calculate the various values using the shells that are given. Like if you have 4s or 2p square like this, then you calculate the value of L, you calculate the value of S and all. So if you remember, from there you had intrinsic spin of electron. Remember, did you ever do this? S is equal to plus half or minus half. Class 11th में करा है कभी ऐसा? You calculated the value of M, you calculated the value of N, whatever was given in the shell. So basically, electrons spin within the shell, which is either, that's why or is written, means either of them will be used. Either it will spin clockwise or it will spin anti-clockwise. Okay, so either of it will be used, both of it is not used. So always we write an or with it. So the intrinsic spin of electron is the, I think, smallest level that can contribute towards magnetic field. Then you have current carrying conductor. Means if I have a wire, this is a wire which is carrying some amount of current. And at a point, let's say here, this point B, I want to find out the magnetic field. I'll be able to find out just by the current flowing, because when a current flows, it acts as a source, as one of the sources of the magnetic field. This leads to magnetism. So you have current carrying conductor. Current carrying conductor. Then directly you have the manufactured magnets present. Magnets are themselves directly a source of magnetism. Like you must have seen, this is the common one is the bar magnet, which you should know, because in chapter 5th we'll be completely talking about the bar magnets. Or you must have seen magnets like this in your practical labs of physics. These are known as horseshoe magnets. Horseshoe magnets. So these are the sources. Then in chemistry, again, you must have studied about the iron ores. Iron ores that directly have the magnetic properties. Basically, you have Fe2O3, you have FeO. So these are the direct iron ores that are existing within the earth that are natural sources of the magnetism. Then we have certain devices constructed when you have the copper wire turns at a certain length. This instrument is known as a solenoid, which is a direct source of magnetic field. Or if I have the turning of the solenoid in the form of a circle, means wire just is turned around in the form of circle, which is known as a toroid. This is also a device that gives rise to magnetic field. So there are various sources of magnetic field, not just a particular magnet. Starting from a very micro level to a major level, you can see all these things and experience. It's not just that magnets are present. And magnetism, the advantage of this chapter is that, see, charges were invisible to us. Feeling charges were difficult, right? You cannot experience it, you cannot see it. But magnets are actually existing, which you can see, repulsion and attraction of the magnet. And magnetic field, you can also feel it. See, if you have two magnets, they do not attract each other unless you bring it at a certain distance. When that distance is crossed, it means the bar magnets, magnetic field lines have been entered. All right. So these things you should know. So about intrinsic spin of electron, that's a part of your chemistry. So this you must have done in your 11th class, and you don't have to go into the details of this. Current carrying wire, this is all about your Biot. We'll be discussing in detail. Regarding the magnets, horseshoe magnet you don't have to do unless your practicals of your school, you see which magnet is there available in your school, because in most of the schools, bar magnet and horseshoe both are there. But regarding the bar magnet, we'll see everything in detail in the next chapter about the bar magnet, your chapter 5th, magnetism and matter. Then iron ores, regarding the iron ores, again, this is a part of your chemistry, their valencies and how they are constructed and all. That's again your chemistry. And solenoid and toroid we'll see in this chapter only, which is just an extension and application of Ampere circuit. So this is what your magnetism is all about. When the charges are flowing, it leads to current, and when current is flowing, it leads to magnetism. That's why we have the magnetic field. That's just a space around the magnet, and it is a complete enclosed loop. Regarding the details of it, that I'll discuss when I'll talk about the bar magnet. So this is what you should know before we actually start with the Biot-Savart law. Now I'll start with that also. Tell me, class, till here, have you all understood? Yeah or no? Okay, Ali, what about Marwa? Aisha, okay. Ubaidullah, did you get it?
Intrinsic spin of electrons. I'm not able to.
You have not done intrinsic spin of electron in chemistry.
I
Type
think I
of
have not
L,
studied in it.
M, S, these things were taken in. Like if I give you, you had SPDF, used to fill the electrons with them to their maximum valencies, S square, like this. Done something like this? No. Is it
I
deleted?
don't know.
What about others? Are you able to catch this? What I said? Like if it is 3p square, so n will be 3 and all. Yes, you have done. And what about others?
I remember.
You remember, Ubaidullah?
Yes, ma'am.
Now you are able to recall. You must have done it. It was there in chemistry. It is there in chemistry. So you have electrons basically spin in one direction. So that's why we write it as minus half or plus half. That's the entire thing that we should know. That's it. So that spinning leads to magnetic field. This is what I just wanted to tell. Okay.
Yes.
Write it. Please write it. Done?
Last one. Done.
Okay, so let's continue with this. Now, this is like your Coulomb's law, the basic law of your magnetism. So this basically says that, let's say we have a wire, and here some amount of current, let's say I, is flowing across this wire. And at a particular point P, I want to find out what's the magnetic field at a certain distance from it. Let's say this distance is some R, which becomes the position vector. Okay. Separation from the source to the point of calculation is what is the position vector. Okay. Now see what we do for our calculations to make the calculations easier and to have a very general formula with us. We choose a very small length that is known as the current element. We have a wire, we just cut it and we choose a very small length of the wire length. A very small length of the wire will be taken. So what will happen if we have any shape we have, we'll just add all of it, and this length can be modified. So that's why we have the smallest length that is possible. So just the length, which is known as the current element, a term is given. So you have to pick out the current element, and the current flows within it in the same direction as that of wire because it's just a segment of the wire. Now, this DL and this position vector will obviously be subtending certain angle, that is theta. Let's come to the law. What does the law say? So I is current flowing through the wire, DL is the current element, R is the position vector of P, theta is the angle between DL and R. Okay, so these are what are all the variables that we are going to use. So according to Biot Savart law, the magnetic field dB means a very small magnetic field. So that small, even a smallest length change can be detected. So it is directly proportional to the current. Okay, directly proportional to the current. It is directly proportional to the current element, which is DL. Current element. Then see, we talked about theta, that's the angle between DL and position vector R. So this will be directly proportional to sine of that angle. Last point, magnetic field is inversely proportional to square of the position. That is, it follows the inverse square rule. This follows the inverse square rule. Like your Coulomb's law, like your gravitational law, where you have R square in the denominator. So this is what it is. Now let's combine it. On combining all of these, I can say dB is directly proportional to I, dl sine theta, but inversely proportional to R square. Here we'll get a constant. When we remove the proportionality sign, we'll put a constant and then we'll write the rest of the things, I dl sine theta by R square. Now look, the constant here, the way constant was 1 over 4 pi epsilon naught, 9 into 10 to the power 9 in electrostatics. Here the constant is mu naught by 4 pi. Now, what is this mu naught? I'll be talking about it. It's the permeability. This we'll see in detail. What is this permeability of free space? But you should know the value of mu naught by 4 pi is 10 to the power minus 7. So we can say mu naught is equal to 4 pi into 10 to the power minus 7. So I can write the final formula as B is equal to mu naught by 4 pi IDL sine theta divided by R square. Whatever value you get, this much Tesla is the final answer. Okay. We will see directions. There are different rules for direction. We'll be following the right hand thumb rule. That's it. No left hand. But first, before going on to that, you should understand what's the meaning of the term permeability. It's very much similar to your permittivity. Just the difference is that permittivity was for your electrostatics. This is for your magnetic. Permeability means something. See, students who have biology, you must have used the term permeable a lot. So permeability means that allows something. Okay, permeability, the meaning of the term is that allows something. So what is allowed here? It basically says that the magnetic field is allowed to change with different materials, with different medium. If you have two magnets, now magnets are easy to comprehend. If you have two magnets in air, they have a very strong force of attraction or repulsion. But if you dip them in water, the intensity is lesser. You change the material, you dip them in glycerine, they'll not be attracted or repelled. So with material, the magnetic field changes. And how is it changing? Depends upon the constant permeability, which is absolute permeability of free space when you put a knot here. Means mu is just permeability of any material. This is permeability of a medium. Okay, so this allows magnetic field to change with medium. Okay, magnetic field to change with the medium. Then mu naught's value, you should know mu naught is particularly for air. So mu naught's value, you should know the way you've written and learned the value of K. This also has to be remembered. That is 4 pi into 10 to the power minus 7. The value is this. So usually mu naught by 4 pi is replaced with 10 to the power minus 7. So mu is the permeability for any medium. When that medium is air, we say absolute permeability of free space or air, that is represented as mu naught. Okay, so mu is the permeability of any medium. Then twice. Mu is the permeability of any medium. And mu naught is just particularly for free space, air or vacuum. All right, so for any other medium that is existing in free space, you'll have a different value. You will use the relative permeability. See, mu, that you have the permeability. Now, if I compare to permeability, means if I compare the permeability of any medium with respect to air, I get relative permeability. You are comparing something. They are relative to each other, relative permeability. So what you can do is in the formula B is equal to mu R into mu naught IDL sine theta divided by 4 pi R square. This becomes the complete formula. Okay, so where mu R is the relative permeability. Now these have a significance when you have in chapter 5th, we will be talking about susceptibility, the permeability, and all many things are there. So when you plot the hysteresis graph and all, relative permeability will play a significant role in the next chapter, but this is just an example that I've taken out from the 5th chapter. For ferromagnetic substances, relative permeability is very much greater than 1. Like iron, it's around 1000. For diamagnetic substances, it is lesser than 1. So there are various kinds of materials. That's why the next chapter says magnetism and materials, right? Magnetism and matter. That matter means it is materials. Ferromagnetic, diamagnetic, paramagnetic, we'll be talking. So there you will see how the values of relative permeability change. Just one more thing, if it is asked in vector form, then the magnetic field will be mu naught by 4 pi will be there. Here you will have I This becomes dl cross r, the two vectors, divided by r cube. This is the formula in vector. See, when you open it, this becomes, what will this be? This will become dl into r into sine theta. And here you will have r cube. That eventually will make it back to dl sine theta by r square, which we have studied in the non-vector form. So this is the formula in vector form. You should go by the cross product of all of it. Now tell me, is the whole story of Biot-Savart law clear? Permeability you've understood? Anything you want to ask anyone? Is it clear or not?
Relative permeability, I'm not able.
Relative permeability means, see, when you are comparing the permeability of any medium, let's say you're comparing oil, or you're comparing honey, or you're comparing glass, any material with air. You're comparing two materials. One is fixed, which is air. Other one can be anything. So you are absolute means when you are not comparing anything. The term absolute you must have studied in your 10th class. Absolute refractive index, relative refractive index. So whenever you have absolute and relative, like your relative velocity, absolute velocity. Absolute velocity is when a car is moving at a certain speed. When two cars are moving, then their velocities with respect to each other change. That is relative velocity. So relative means when you are comparing it to something. Okay?
Yes.
Please write it, all of you.
Done.
Yes, Ubaidullah.
This is relative magnetic field.
Mu R is. Mu is for a material. Naught is for air. Mu by mu naught. This mu R is the relative permeability. So see, mu will come instead of mu. I have written mu R into mu naught. Got it?
That is not mu. That is mu.
What? Where?
That is mu by mu not.
Yeah, this is mu by mu. This is for a material. Okay, you can write mu m so that you remember. So the formula technically would have been mu m idl sine theta divided by 4 pi r square. Now instead of this mu m, these could be multiplied mu r into mu naught. That's what I've written because you will be provided with the relative permeability rather than the material's permeability. Okay.
Yes, ma'am. Ma'am, can you scroll up?
All those who have written, you can leave. I'll continue this in the next class. All right. Okay, then. Thank you, class. Goodbye. Ferromagnetic part. Okay, Aisha. See, regarding the ferromagnetic part, I was just saying that there are certain materials that we'll be studying about in the next chapter in detail. Okay. So ferromagnetic, I've just given you an example that relative permeability will be used there. So relative permeability is very much greater than 1 in case of ferromagnetic substances like iron, which is having the permeability more than one that is around 1000. Likewise, diamagnetic. So this whole table, we'll do it in the next chapter. I was just giving a small example. You don't need to go into the details of it or remember it here, or you have to learn it in the next chapter. Okay.
Thank you. And that is equal to 1000 for iron.
Yeah, that is approximately equal to the similar sign, no? Approximately equal to 1000.
Yes. What is diamagnetic?
See, don't go into the details because see, there is a lot to understand for these. There are magnetic properties that you need to know. Just understand it's just classification